Now, that was sort of the introduction. We're going to talk about terpenoids now. Now, terpenoids are a very large class of compounds, and terpenoids are classified based on how they are made. So it's not based on anything else, so there may or may not be similarities between the different classes of terpenoids. But it's based on the structure and how it's made. Now, terpenoids, I'm going to use the terms terpenoids and terpenes interchangeably, okay? And I just found a typo. There we go. So, if you want to be precise in the definition, a terpene is basically a compound that's 100% hydrocarbon. It all contains just carbons and hydrogens. A terpenoid has been modified slightly and an oxygen molecule has been added to it. So when you add an oxygen molecule, it makes it just a little bit more polar, but it's still going to be primarily fat soluble. So terpenoids or terpenes, they'll use those terms interchangeably. They're classified based on how it's made, and the structure on the left is called isoprene. This is a 5-carbon structure, and this is the basic building block. It's like the very smallest Lego piece that you use to make the terpenoids or terpenes. So there are different classes of terpenoids, and it's based on how many of these isoprene units are stuck together to make them. So a monoterpene has 2 of these, a sesquiterpene has 3, diterpenoid has 4, triterpenoid has 6, and tetraterpenoids have 8. And that's the basic classification of the different ones. And so you could have, a terpenoid could have anywhere between 10 and 40 carbons, roughly. You could even have more than that as the basic building block. And then we also can classify the different types of terpenoids into other sort of categories. So we'll go ahead and we'll just go through the different ones now. So the take-home message with this slide is terpenoids are made based on how many isoprene units they have, and the basic isoprene unit, the rule is the terpenoid will always consist mostly of divisions of 5 or multiples of 5. So 5N, so you have 2, 5N, if it's basically 5 times 2 gives you 10 carbons, that's going to be a monoterpenoid. We'll go from there. So here we've got an example of the blue and the red are the isoprene units, and they're attached to something else. Don't worry about that. You stick them together, then you've got the first thing showing up there is the beginning of a monoterpenoid, and then what's shown on the 6 isoprene units stuck together gives you a compound called squalene or squalene, and this can be moved around to make basically steroid compounds, and that would be a triterpenoid. So here's sort of a breakdown of some ones that we're going to go into a little bit more detail on in a second. So the monoterpenes or monoterpenoids, this is where you take 2 isoprene units, stick them together, and then you get a compound that you move it around and kind of shuffle things around, make a little circle out of it. And this is where you get, for example, this pathway here produces alpha-pinene. This is the main monoterpene that you get in turpentine. So turpentine is basically made primarily out of alpha-pinene, some beta-pinene, there may be some eucalyptol or something else in there, but that's the main compound. And that is a true monoterpene. There's not a single oxygen attached to that, so that's a monoterpene. So monoterpenes usually have 10 carbons. You could, technically speaking, add some extra ones on afterwards if you wanted to, but the basic building block is a 10-carbon structure. The classic monoterpenes that we'll talk about is menthol. This is the active ingredient in peppermint oil. Carvacrol and thymol are found in thyme and oregano oil. Camphor is comes from the camphor tree, and it's primarily found in sport creams and muscle pain creams. Eucalyptol, which is found in cough drops and also in various chest rubs for colds and flus, is also found in sports muscle rubs as well, is obtained from eucalyptus tree. Terpene-4-all is the essential oil that's primarily in tea tree. It's also found in juniper oil as well, so if you drink any gin, you're probably consuming a little bit of tea tree oil internally. And so those are some classic monoterpenes. As we mentioned before, these are also going to be essential oils. So these are going to be obtained from these trees. The main actions associated with essential oils is going to be an antiseptic, antimicrobial. It'll act as a counter irritant, so if you apply it topically, it'll make the skin go red because the capillaries will dilate. It acts as a carminative, so it increases digestive function, relaxes smooth muscles, helps with gas. Can act as an analgesic, so some of these will bind to cold or hot receptors in the skin and decrease pain. And then finally, some of these will act as expectorants. So if you inhale them or drink them internally, they can have a slight irritating effect to the mucous membranes, increase mucus production, and then help to cough up phlegm. So lots of different actions associated with these things. But if you knew that a plant contained high amounts of monoterpenes, or if someone was taking an essential oil capsule that contained a lot of monoterpenes, then you know by default these are going to be the main actions associated with it. It may not have all these, but it probably will have most of these actions. Okay. So on the left-hand side, there's a picture of eucalyptus tree, and if you crush up the leaves, it's very aromatic, lots of wonderful smells coming out of it. And one of the main active compounds in there is going to be eucalyptol, which is shown on the bottom left. Now, one characteristic of these essential oils is they're volatile, obviously. These monoterpenes are going to be volatile. They're also going to be colorless, and something to be aware of when it comes to pigments. What gives substances color is how many double bonds they have that are conjugated in a row. So if you got double bond space, double bond space, double bond space, it'll absorb a certain wavelength of light. So you won't see a lot of colors with the monoterpenes or the sesquiterpenes, but when you start getting up into the tetraterpenoids, you're going to actually start seeing more pigments, and also in some of the ones before that as well. But so for example, the carotenoids, beta-carotene, these are tetraterpenoids. These are very large compounds that have a lot of conjugated bonds, and they have color associated with it. But very small molecules don't have color because they're not absorbing in the visible spectrum and reflecting it. And then the final thing with all terpenoids in general is that they're non-polar. So if you want to extract these substances, water is not the best way to do it. Now, just as an aside, if you have a cup of peppermint tea, the peppermint oil will not actually go into the water. It just sort of stays at the surface. So you can drink it and then get some peppermint oil into you, but it's biphasic, generally speaking, if you let it settle long enough. So water is not the best solvent, but yes, you can make tea with peppermint and it still has medicinal effects. So here's thyme and mint on the left. Those are both in the mint family. The compounds in thyme and oregano oil are shown at the bottom, the thymol and carbachol. Menthol is the main active thing in mint, but you do find it in other plants as well. And then camphor laurel, which is related to cinnamon, is where you get camphor from. So we're now going to talk about a subclass of monoterpenoids, and these are the monoterpene or monoterpenoid lactones. Now, lactone is highlighted on the left-hand side there. You can see it in the green. That's basically a lactone group. It's kind of a carboxylic acid with an ester-like bond on it. Now, what I'm showing at the top there is an iridoid. So there are two different types of basic backbones that you can get for monoterpene lactones. It could be an iridoid or a secoiridoid. Now, iridane is shown in the middle. That compound was originally extracted from a certain type of insect or ant. And then secoiridoid, iridane is slightly different. rather than having the ring structure, it's open entirely. Now what happens is, if you stick a lactone and close up those rings, you either get the sort of the basic iridoid compound shown at the top, or you get a secoiridoid. And we'll talk about those in a second. So these are monoterpenoids. So I want you to remember that they contain 10 carbons. So basically, if it's got 10 carbons, it means it's made from 2 isoprene units, because 2 isoprene units, that means it's 2 times 5 carbons, gives you 10 carbons. I want you to also remember that a lot of these iridoids exist as glycosides. And so sometimes sugars are attached to these guys, and they don't make the best volatile compounds. Once you start adding a lot of oxygens to them, even though they're only 10 carbons in size, the oxygens weigh them down, and it also forms polar bonds with water, so they don't really want to evaporate as easily as like alpha-pinene, which is in turpentine. From a medicinal standpoint, these don't have quite the same actions associated with the other monoterpenes and terpenoids. They tend to have a bitter action. That iridoid compound, or that lactone group, in general, when you hear lactone when we're talking about the phytochemicals, it's probably going to taste very bitter. So monoterpene lactones and sesquiterpene lactones always have this bitter taste associated with it. So the other benefits or actions associated with these compounds is they possess an anti-inflammatory effect. So when you think of things like the anti-inflammatory effects of olive oil, it's not entirely related to an iridoid, but it does have some of its anti-inflammatory effects may be associated with this. Also, they have vulnerary effects as well, so they can help speed up the healing and decrease inflammation of things. So, 2 examples of things that we've talked about already. For example, I don't know if we talked about this or not, but an iridoid glycoside shown at the bottom there is a harpagoside. This compound is a glycoside. You can see there's a sugar on the left. You've got the iridine molecule there, and that's basically your monoterpene lactone. And then it also has another compound, a phenylpropanoid. We'll talk about those later on, attached to it. So it's got 3 different groups of compounds attached to it. This is found in a herb called devil's claw that originates in South Africa, and it's used to promote digestion because it does have some bitter actions associated with it. And this harpagoside, I want to give you a hint for the glycosides. Most glycosides, compounds that have sugar attached to it, they'll end in side, S-I-D-E, generally speaking. Not always, but generally speaking. So if you hear something's some kind of side, it usually means it's a glycoside. So this compound in devil's claw has anti-inflammatory effects and is often used traditionally in herbal medicine. We now use it in Western herbalism. You find a lot of products have it, and also in South African medicine for treating arthritis and other types of inflammatory disorders. Aucubin, which is shown on the right, is another iridoid glycoside. And you'll find this compound in, for example, plantago species, so plantain, greater plantain, broadleaf plantain. It's used in Western herbalism. You apply it topically for wounds, speed up the healing. It can be taken internally for stomach ulcers. So it has, and it also can have an anti-inflammatory effect. So the properties of these 2 compounds is mostly anti-inflammatory and also some vulnerary actions. Now, 2 examples of secoiridoids here is amarogentin, which is found in gentian lutea. This is a very, very bitter compound. It's a mixture of a few different things. There's a glycoside on there, a sugar attached to it, but that compound there is extremely bitter, and so it's used primarily to promote digestion as a bitter tonic. Gentian also has some antimicrobial properties as well, and so it may be attributed to these compounds. Now on the right-hand side, you see a compound called oleoropin, and this is basically a combination of a sugar attached to a secoiridoid attached to a phenolic compound. So these compounds are getting kind of complicated. That oleoropin compound, it has a lot of anti-inflammatory effects, and it may be related to the sesquiterpenoid and or the phenolic compound attached to it. But you will find that in olive leaf extract, and there will be small amounts of these compounds, especially the sesquiterpenoid. Once you remove the sugar, it's going to be found in olive oil as well. So those are the monoterpenoids. So to summarize, you've got 2 carbons. Most of these are going to be essential oils. And then you've got the iridoids and sesquiterpenoids, which are bitter in taste, and they're often attached to sugars and exist as glycosides and have anti-inflammatory and anti-inflammatory effects. Anti-inflammatory and vulnerary effects. The next group of compounds we want to talk about are the sesquiterpenes. Sesqua in Latin or Greek basically means half, so or 1.5. So a sesquiterpenoid basically refers to a compound that has, if a monoterpenoid has 2 and a diterpenoid has 4, this has 3 isoprene units, so 15 carbons in total. And there are a number of sesquiterpenes that exist. For example, humulene is found in hops, which you get in beer. Caryophyllene is found in clove. Zingiberine is found in ginger. Now, in ginger, the main active compound that's researched is gingerol. That's what's typically has a lot of the effects on the serotonin receptors to act as an antiemetic. This compound, gingiberine, is an essential oil. It does evaporate to some degree. It'll have a higher boiling point than the monoterpenes do. I'm sure it has carminative action, some other benefits. So I think that ginger has many different compounds in it beyond just the gingerol that has active effects. So with regards to sesquiterpenes, you can see none of these guys shown here have oxygens attached to it. So these are pure sesquiterpenes. You don't need to know the structure of any of these guys. I'm assuming that we know that some of these compounds have anti-inflammatory and carminative actions. They're volatile, they're still colorless, they don't dissolve in water very well, and that's basically the summary of what these guys do. Okay? Now we talked about the monoterpene lactones. I also want to talk about the sesquiterpene lactones. These are very important compounds. Again, lactone, when you hear lactone, think bitter. So these are going to be very bitter compounds, and the sesquiterpene lactones are a really neat group of compounds. A lot of these are found in the Asteraceae family. This is a common classic family that includes those flowers that have basically, they look like flowers where you've got the little dot with the petals that go around it. That's the sesquiterpene, or that's the Asteraceae family, the aster family. And sesquiterpene lactones, again, they have 15 carbons, and they also have that lactone group. So when I think of sesquiterpene lactones, the very first thing that comes to my mind is bitters, so digestive bitters. Second thing I think of, antimicrobials. A lot of the really important antibacterial, antifungal, antimalarial, anthelmintic compounds are related to sesquiterpene lactones. Also, there's research that shows that a lot of the time with the antimicrobial compounds, they often have some anti-inflammatory effects associated with them as well. And then finally, many of them have some anti-cancer effects, because when something decreases inflammation, it usually has some benefits for cancer as well. Now, wormwood, which we've described already, it's the plant that you make absinthe, the digestive bitter, from. It's usually used wormwood combined with fennel or anise. The bitter compound, or one of the compounds in this, is absinthin, which is shown at the bottom there. Now, if you actually go and count the carbons, there's 30 carbons on that structure there, but what it is a dimer of 2 sesquiterpenes basically stuck together. Okay, so two sesquiterpene lactones stuck together. So it's a derivative of a sesquiterpene lactone. When we talked about artemisinin, which is an anti-malarial drug, it was derived from sweet wormwood. It's a sesquiterpene lactone. Another example is matricin. which is shown at the bottom there. That's one of the main active ingredients in chamomile. And you can see, if you go and count, the pink structure has 15 carbons. Now, there's on the right-hand side of that structure, there's basically a little acetyl group that's been added to it. So it will have more than 15 carbons. It actually has 17 carbons, but that was added after the sesquiterpene was made. You can add things on later on. You can add sugars, you can add acetyl groups to it, and it can change the functionality a little bit, but the basic building blocks for that were 15 carbons altogether and a lactone group on there. And so chamomile, it does have a little bit of a bitter taste when you drink chamomile tea, and that compound there I think is important for its pulmonary effects. So chamomile, it has benefits for digestion, it has an antispasmodic and anti-inflammatory effects, and I think many of the benefits, but not all of them, are associated with this compound here. So another example is parthenolide. This is one of the main active ingredients in feverfew. Feverfew is traditionally used to lower fevers, so with people who have really high fevers, but it's also used for treating migraines. And the active ingredients, one of them, because I think there are numerous ones, are related to the parthenolide compounds, and these are sesquiterpene lactones, very bitter. This compound also has been shown to have some activity against leishmaniasis, which is a type of parasite from tropical that you find in tropical countries. So feverfew, the main actions for migraines, but it does have some bitter anti-inflammatory effects as well associated with these compounds. And then on the right-hand side, we've got chicory. So chicory is used as a digestive tonic. The roots are ground up and toasted and often is used as a coffee substitute. The bitter quality associated with chicory is related to lactucin. Now, lactucin is a sesquiterpene. You also will find this in, if you look at, for example, what do you call that? Romaine lettuce, certain types of lettuce. When you break the lettuce and you get that white bitter resin that comes out of the leaf, that usually contains lactucin. It's a latex that contains lactucin. And so it's one of the compounds that gives lettuce and chicory its bitter properties. And so it's a good digestive tonic, but I'm sure there's other actions associated with it we don't even know about now. So when it comes to the sesquiterpene lactones, the take-home message there is you've got 3 isoprene units, 15 carbons, and when you've got the lactone added on, you get that bitter property, and it has a lot more anti-inflammatory and antimicrobial actions associated with it. The diterpenes, or diterpenoids, this class of compounds I find is a little bit harder to make some generalizations about, because there's lots of different compounds that fit into this category, and they have different actions. To give you a couple examples, diterpenes, you should be able to figure it out already. If the monoterpenoids, mono meaning 1, has 10 carbons, then the diterpenoids has twice as many, and that gives you 20 carbons. So you basically, diterpenes are made from 4 isoprene units. A couple examples of some classic phytochemicals that are diterpenoids. Tetrahydrocannabinol is, or THC, is the main active ingredient in marijuana, and so THC is a type of diterpenoid. And another example is steviol, which is an artificial sweetener found in the plant called stevia. It also has this diterpenoid structure. So lots of different actions associated with these compounds. THC has some neurological effects. It also has some antiemetic effects. It may have some immunomodulating effects. Steviol, I think it just has a artificial sweetener taste. It may have some other effects. Some of these diterpenoids are volatile. Some of them aren't. They're all nonpolar. So making a cup of tea with marijuana, you probably wouldn't be able to extract the THC because it's because it's non-polar. It's not water soluble. Typically, the way that people extract THC from things is they could use, for example, if they wanted to use marijuana in baked goods. If you're making cookies or brownies, you may take the plant and boil it in water with butter, and the THC, which is fat soluble, will go into the butter, because the butter will act as a solvent for the diterpenoids. And then you could cool it down, scrape off the butter off the top, and then you basically, it's a way that it can be extracted that way. To, if someone was taking recreationally or medicinal marijuana, they may not want to smoke it because of the damage to the lungs, but they may cook it in that fashion. So that would be one way you could extract it. You could use olive oil. You could make a tincture, and a tincture will dissolve some of these diterpenoids, but alcohol is more polar than non-polar, so it's not the best solvent for these guys, but you can get a little bit of these guys going into solution because alcohol does dissolve non-polar things to some degree. So stevia is on the left-hand side, THC is at the bottom left. Salvinorum A is a diterpenoid that's found in diviner sage, or Salvia divinorum. You may have heard of it. It's a member of the mint family, but it's used by a very small group of shamans in Mexico, and it's usually the diviner sage or Salvia divinorum is chewed in the mouth for big mouthfuls of it for long periods of time. And it has a very slight, has a significant hallucinogenic effect. It's technically legal in Canada, although it probably shouldn't be. I think it's just flying under the radar of Health Canada. And if you go into certain marijuana dispensary stores, or stores where, like those rock shops where you can buy pipes and scales and Iron Maiden t-shirts and whatever kind of stuff related to rock and roll is, there's extracts that they sometimes sell there, and this is often smoked, and it has a very potent hallucinogenic effect. And I wouldn't recommend doing these things. I think it's very scary when you look at the shamanistic use of this. It's not smoked in a pipe with a high temperature torch. It's basically chewed to get a slow release. And the reports of people doing this Salvia divinorum plant is it basically teleports into like another dimension, and they sometimes will have no recollection that they've even done the salvia, so they get very confused when they're doing it. And I had one patient who was doing it on a daily, someone gave it to him for his birthday, and did it every day for a week. And when you smoke it, the high only lasts for about 10 minutes, 15 minutes. But it can leave the person feeling very confused and disoriented and disconnected, because it feels like they've woken up from a dream, but they can't figure out what reality is. And so this guy actually ended up going temporarily insane, and he ended up having to get committed to a hospital because he kind of lost sense with reality. So I could see the potential for this really triggering certain mental disorders like schizophrenia, because again, it's being used at a concentration and in a fashion that's very different than maybe the shamans in Mexico were using it. What's interesting about Salvia divinorum is that, unlike magic mushrooms, ayahuasca, peyote, it doesn't interact with dopamine or serotonin receptors. It actually interacts with a type of opioid receptor. So opioid receptors, usually I think of those when I'm thinking of potent, strong painkillers, the opiates like morphine, codeine, opium. But it doesn't have any of the analgesic effect, any of the pain relieving effect. It binds to a very certain subcategory of receptors that it doesn't relieve pain, but it causes changes in consciousness and awareness. So it's a completely different hallucinogen than anything else that we've described so far. And if you know anyone who's taken high doses of opiates, often they'll kind of lose touch with reality, and it's because of these receptors that the opiates can interact with. And so the Salvia divinorum, it interacts with those receptors. So just as a side note, there's another example of a substance that's interacting with the nervous system. Salvinorum A interacts with certain opioid receptors. THC interacts with cannabinoid receptors. And then I believe this Videozen A compound at the bottom, it might affect dopamine receptors. It's found in Vitex. I don't know if it's the main active ingredient or if it's the flavonoid in Vitex that modulates the dopamine receptors, but it may have some hormone regulating effects. So the take home for the diterpenoids, hard to make a generalization, but definitely it does have potential to have some neurological effects. Now, the next group of compounds we want to talk about are triterpenoids. So you add up your isoprenes. We're at 6 isoprenes now. That gives you 30 carbons. And typically triterpenoids, they can exist in a single linear form like squalene that we described earlier on. I don't know what medicinal properties it has, but usually they cyclize and form some type of multi-ring structure. And so when it comes to the different types, you can have one that has 5-membered ring or a 6-membered ring. Now, the tetracyclic compound in the upper right there, you've got 3 6-membered rings and a 5-membered ring. That's a basic backbone for a steroid. So these triterpenoid compounds have the potential to interact with steroid hormones and modulate them. We'll get to that in a second. So one example of a triterpene or triterpenoid that is not steroidal, it doesn't have that steroid backbone, is something like ursolic acid. And this is a compound getting a lot more attention in research right now. It's found in lots of different fruits and vegetables. So apples have fairly high amounts. Now, the red color of the apple has nothing to do with this compound. This compound does not have a significant color associated with it, but it's found in lots of various berries, spices, fruits, and other plants. And ursolic acid, I've just chosen that one in particular. Studies done with that have been basically illustrated that it has an anti-inflammatory effect. It may have some benefit against cancer, viral infections, may have a protective effect on the heart. And so you're probably getting small amounts of this when you're eating a diet rich in fruits and vegetables. And I don't know of any supplement forms of ursolic acid, but I think there could be potential for this compound in the future. It's a very large compound. So unlike the monoterpenes and sesquiterpenes, and even the diterpenes, the larger you're getting, it just gets too heavy. So triterpenes and triterpenoids, they're not going to evaporate. They're just way too big. Even the diterpenoids don't really want to evaporate. It takes quite a bit of heat to get them off to evaporate. So these compounds, they won't evaporate and they don't dissolve very well in water. This is just a random study I found about ursolic acid. Now, there are another group of compounds called triterpenoid glycosides, or saponins. Now, we've already mentioned saponins earlier. So if you look at glycyrrhizin, which is in licorice, it's a saponin. Here you've got a triterpenoid. So it's a very large compound, consists of roughly 30 carbons. That's the backbone. It'll basically have 30 carbons. And it's got a couple of sugars attached to it. And so what happens is the sugars form the polar component, and then the aglycone component, which is glycyrrhetinic acid, forms the non-polar component. And so when you have a polar and a non-polar component on the same molecule, it has the potential to act as a soap. So this is basically an amphipathic compound that's both water and fat soluble that will form a soap. And if you look at the left-hand side, I took a bunch of chunks of licorice root, added it to some water, and then shook it up. And you can see it foams up. Those are the saponins. Those are the triterpenoid glycosides making soap. And so these saponins have a number of effects in the body. One, they can be a little irritating to mucous membranes. If you were to inject them directly into your bloodstream, it could potentially cause red blood cells to lyse, which wouldn't be good because it would just basically disrupt the cell membranes and they would fall apart. But taking them internally, many of these things can have anti-cancer effects, anti-inflammatory effects, antiviral effects. So different things. Now, they're non-volatile still, but they are water soluble, which is interesting. And what's I think is kind of neat about saponins like licorice is it dissolves in water. But in Chinese medicine, often licorice is added to a lot of different formulas because they say licorice helps the other herbs enter the meridians. And so from a chemical standpoint, what I kind of wonder is Chinese medicine, they don't use tinctures. And so if you're trying to extract phytochemicals that are fat soluble, and you're trying to use mostly decoctions, water-based extraction processes, licorice might help act as a soap to help dissolve some of these compounds to get them to go into the water better. So licorice is an example of a herb that could help other phytochemicals go into solution. So again, this is a glycoside. You've got your glycyrrhizin, which is the glycoside. Through hydrolysis, you release the glycyrrhetinic acid, which is your aglycone, and then in this case, you've got glucuronic acid. There's two molecules that are the glycone component of it. Now, the next group of compounds I want to talk about are steroidal saponins. Steroidal saponins basically means you've got a triterpenoid that has a steroid-like backbone, and that's going to be the 3 6-membered rings attached to the 5-membered ring. And these compounds, they too are amphipathic, so they can form as like basically a soap. But because they have that steroid backbone, they're going to modulate various steroid hormones in our body. So this is going to be things like cortisol, estrogen, progesterone, testosterone. And so there are a number of herbs. Excuse me, I sneezed, but I was able to get the mute button off first. So there's a few different types of compounds. Most of the adaptogens that we've talked about already, the classic adaptogens are steroidal saponins. And these would be things like astragalosides and ginsenosides. And you can see the pink structure on the right-hand side is the basic backbone for this steroid, and it has sugars attached to it. So Korean ginseng, which is shown on the left, it has ginsenoside RB1. Eleuthroxide A is another example. It's got a steroid backbone. These are example of your adaptogens. So they modulate the immune function. They can have an effect on hormones. They may lower cholesterol, lots of different things they can do. Because cholesterol also has that steroid backbone as well. And I'll do one final one. The triterpenoids. If you look at digoxin, this is your cardiac glycoside. This is a steroidal saponin, but primarily it's referred to as a cardiac glycoside. So it has that steroid backbone. It does not have any adaptogenic properties because it has such a positive effect, strong effect on the as a positive ionotropic compound and a negative chronotropic. So what that means is it increases the force of contraction because positive means more ions are getting into the heart, causing stronger contractions, and negative chronotropic, chrono meaning time, it slows down the heart rate. So something that's a positive ionotropic and negative chronotropic means it increases the force of contractions and slows the heart down. Now, just as an aside, many of the adaptogens will also have some affinity for the heart as well. It's not a major indication, but they can be used to help improve edema, which is what happens when you have pooling of water in your ankles. And so, although many of the ginsenosides, astragalosides are not classified as steroidal as cardiac glycosides, I think they do have some potential to have a mild cardiac effect. So class is over now. So the tetraterpenoids is where I'm going to start off next week. If you have any questions, let me know. I'm going to check really quickly here.